Hello everyone, I'm Sindhu Hegde, and today I'll be presenting our work on multilingual visual speech recognition. Let us begin by first understanding what exactly is the task at hand. In visual speech recognition, also known as lip reading, we will have a silent video of a person speaking given as input. Some of the examples are shown in the slide. Now, the goal is to transcribe what is being spoken in these videos solely from lip movements. Now, the question arises as to why is lip reading important? Well, there are several benefits and scenarios where reading lips becomes a crucial necessity. For example, relying only on audio signals in noisy environments will not lead to satisfactory results, whereas lip movements are unaffected in the presence of any background noise. Lip reading has applications in historical settings, like recovering speech from important historic videos. For example, Sir Churchill's resignation video, as shown in the slide, or in recovering old films. Further, lip reading can be used in medical applications where people with aphonia or other voice disorders can communicate through lip movements. Another use case of lip reading is in curating sign language datasets. In sign language, signers often mouth the words. Thus, lip reading can assist in automatic annotation of sign language datasets. Now that we have seen the importance of lip reading, let us quickly review how the field has evolved. In recent years, lip reading has received tremendous attention. Multiple works have been proposed which have pushed the boundaries of lip reading models. The current state of the art network achieves a word error rate of around 13% on one of the most popular English lip reading datasets called LRS3. However, it is important to note that today's lip reading models are accurate only for English. For other languages, like Spanish for instance, the word error rates are very high, in the range of 50s. One of the main reasons for this inferior performance can be attributed to the lack of multilingual lip reading datasets that are publicly available today. When compared to English, which has more than 3,500 hours of training data, non English languages, including Spanish, French, and a few others, have very limited data, around 300 hours each, which is an order of magnitude smaller than English datasets. Thus, in our work, we propose to scale multilingual lip reading with the help of three key advancements. First, we curate and release a large-scale multilingual lip reading dataset termed MultiVSR, which comprises about 12,000 hours of video data. This is the largest multilingual lip reading public dataset available to date. Second, we develop a multitask network which can perform two tasks in a single framework, identifying language from lip movements and transcribing what was being uttered. Third, we train this multitask model jointly across all languages. This is in contrast to existing works where each language has a separately trained model. Let us now closely look into our new dataset, MultiVSR. MultiVSR includes English plus 12 other non-English languages. Among them, we have 9 high-resource languages, meaning the amount of data available in these languages is over 200 hours per language. The other 3 are low-resource languages, where around 100 hours of data is available per language. The dataset is automatically gathered from publicly available YouTube videos. Some of the statistics of our final data is shown in the table here. MultiVSR is a massive dataset with a huge diversity in terms of the speakers as well as languages, totaling up to 12,000 hours of video data. To create MultiVSR, we start with raw YouTube videos. Once we collect these videos, the next step is pre-processing. Our pre-processing pipeline involves two stages. First, person tracking and cropping, and second, synchronization detection. We start by resampling the videos to 25 frames per second and detecting faces in each frame. We then track segments where the face is clearly visible. We also perform a few filtering steps like discarding short clips, which are less than 1 second, and discarding low resolution clips where the resolution is below 96 cross 96 pixels. And finally, we crop the videos, which together forms the first stage of our pre-processing pipeline. Next, in the synchronization stage, we verify whether the visual crop is synchronized with the corresponding audio segment. To do so, we use a pre-trained model called SyncNet to calculate synchronization offsets and discard the crops where the offset is about 10 frames. Our entire data collection process requires no manual efforts because all the steps, including label generation, are automatically done. To generate the text labels, we rely on audio signal. We first identify the language using an audio-based language identification model called Voxlingua. We then generate word-level time-aligned transcripts using the pre-trained WhisperX ASR model. So here is a summarized view of our data pipeline. We start with data collection as shown here in step A. We then perform person tracking and cropping, which is the step B, and finally proceed to the filtering stage using synchronization detection, which forms the step C. Our final data after automatic transcript generation includes approximately 1.6 million video clips across 123,000 YouTube videos. Here are some example clips from MultiVSR.
You get is the same idea as going up to the forest.
Today, I want to teach you how to talk about your profession and your job.
Can I compare thee to a summer's day?
Vamos a pasar un poquito a lo que es la pantalla. Temos os demonstrativos. Olha, a classificação demonstrativo.
Ben al di sopra di qualunque altro telefono abbia mai provato. Ora.
Okay, let us now proceed to explore our architecture. We design a multitask encoder-decoder model as illustrated in the figure. The input to the model is a sequence of silent video frames, and the objective is to predict the language token as well as the corresponding text sequence in a single framework. From the input video, we start by extracting the visual features using the pre-trained Visual Transformer Pooling or VTP model. VTP serves as a robust visual backbone and outputs per frame lip movement features. The VTP features act as input to the transformer encoder, which temporally encodes these to produce the encoder embeddings. This is followed by transformer decoder, which cross-attends to the encoder and generates decoder embeddings. Finally, the network autoregressively predicts both the language token as well as the text sequence using beam search. So this was a brief overview of our network. Please refer to our paper for more details. To train and evaluate our multitask network, we leverage our newly collected multi-VSR dataset of approximately 12,000 hours. A single model is jointly trained on the 10 high-resource languages, which constitutes around 11,500 hours. The remaining 3 languages contain about 100 hours each and are used to evaluate the performance on low-resource languages. We train and test the network for 2 tasks. First, lip reading, and second, visual language identification. Moving on, let us now see some of the results. For the first task of lip reading, we compute word error rate and show the results on MultiVSR test set. We compare with the existing state-of-the-art multilingual lip reading network and also report the performance on monolingual models where an independent model is trained for each language. As we can see from the table, our multilingual model clearly outperforms these baselines by a significant margin. The gains can largely be attributed to two factors. First, the larger number of hours in each language in multi-VSR train set, and second, joint multilingual training across all languages, which further increases the data scale. Now, for the second task of visual language identification, we report the accuracy of identifying the language from lip movements. Notably, we do not train a separate model for this task. Instead, it is learned jointly during the lip reading training process. Again, in comparison to the existing work, we can see that our joint model achieves a very high accuracy across all languages. Next, we also showcase a few qualitative examples demonstrating the effectiveness of our model. The ground truth language and transcription is shown in red initially, followed by our model's prediction in green. Note that the audio is played here only to verify if our prediction matches the ground truth.
Are perceived in the world in a particular way.
On va parler en français. Entiendo, estudio hace 15 años.
Here are a few more examples from our model. And another point, note that all these samples are from unseen identities. The model has never seen these people during training. Thus, the results indicate the true capability achieved by our multitask network.
But I just felt so inspired, It was an improvisation. Determinante na minha história musical e
Parla un po' italiana, sai?
Ecco.
Sì, io.
Another interesting use case of our large-scale data, as well as the network, is in extending it to more languages, especially languages with limited amount of training data. For this study, we consider the 3 languages as explained before, each with about 100 hours of training data. Fine-tuning our joint pre-trained model produces very good results. As we can see in the plot here, fine-tuning with as little as 25 hours already yields a word error rate of around 60%, which consistently improves when more data is added. This demonstrates the power of leveraging large-scale multilingual pre-training to enhance lip reading performance, setting the stage for broader and more inclusive applications of visual speech recognition. All our codes and pre-trained models have been released. Please check our webpage. Thank you for watching.